Welcome all. In today's class we are going to learn the calculation of radius ratio in tetrahedral void, and we are going to solve some problems on this concept. The tetrahedral site or tetrahedral void is formed by placing a particle over a trigonal void. Now in this particular diagram, if ABC is lies in one plane and it is forming a trigonal void, and in that trigonal void if I keep a D particle, then within this particular two layers whatever void is created, which is represented here by a gray ball, which is called tetrahedral site, and normally the cations will occupy these voids. So let us consider one simple example, that is zinc blend contain zinc sulfide. In this case, sulfide anion, that is S-2, occupies the alternate corner of a cube and they touch one another. So in this diagram, this blue color balls indicates sulfide anion, and the tetrahedral void created is occupied by zinc plus 2 cation, which is represented by gray ball. So let us consider this particular tetrahedral structure and let us calculate radius ratio in this particular case. As we know that in case of tetrahedral void formation, the particles, that is anions, will occupy an alternate corner of a cube, and our cation is placed at the center of the cube as shown in this particular diagram. Let me consider A is edge length of a unit cell, R plus is a radius of a cation, and R minus is a radius of anion. Now in this particular diagram, the face diagonal, that is from this corner to this corner, is called face diagonal, and we know that these corner particles are in contact to one another, and hence face diagonal is equal to, this is a R minus plus R minus, so which is equal to 2R minus. And if I apply a Pythagoras theorem to this face diagonal, then I can get a face diagonal in terms of edge length A is equal to root 2 into A. So we get this relation now, face diagonal which is equal to 2 times R minus is equal to root 2 into A. So R minus is equal to 2, I am shifting to other side, so it will be root 2 A upon 2, root 2 gets cancelled, so I get R minus is equal to A upon root 2. So this is our equation number 1. From this diagram, we know that a body diagonal is in terms of A is root 3 into A. So BF, let us consider BF. See this point, let us consider F. So BF is equal to root 3 into A. But as we know that our cation is situated at the center of unit cell, so the distance BE is equal to half of BF. Since we know that this BE is nothing but this radius of a anion, that is R minus plus R plus, that is the radius of cation, which is equal to, this is a half of body diagonal, so which is equal to half of BF. F is this particular corner particle, so half of this BF is equal to BE. So half of BF, as we know BF is root 3 into A, substitute. Now R plus plus R minus we get is root 3 upon 2 into A. Let us call equation number 2. Since now we have equation 1 and equation 2, now we divide equation 2 by equation 1. So on left hand side we get R plus plus R minus divided by R minus equal to root 3A upon 2 divided by A upon root 2 So we know that denominator of denominator goes to the numerator, so we will multiply by reciprocating that, so that is root 2 upon a. Now a gets cancelled, root 2 and here root 2 gets cancelled, so remaining is root 3 upon 2. In the next step I will split left hand side term, that is r plus upon r minus plus r minus upon r minus equal to 1 equal to root 3 is 1.732, root 2 is 1.414. After dividing these two terms I am getting 1.225. I will shift 1 to other side and simplify, so I get limiting radius ratio of tetrahedral void is 0.225. That means whenever a cation has a radius ratio value, it is more than 0.225, it is going to show tetrahedral void or tetrahedral structure. The effect of increase or decrease in radius ratio on a coordination number and the structure of ionic crystal. So let me consider an octahedral void. As we know, in octahedral void the cation is placed within the octahedral structure. So this is our octahedral void where radius ratio of the cation is lies between 0.414 to 0.732 and its coordination number is 6. Now there are two possibilities I may come across. The first possibility is, if suppose I am having a cation whose radius ratio value is less than 0.414 and still if I force it to place in this octahedral void, then what is going to happen? So as we can see in this left hand side diagram, so as the radius of a cation is smaller, as a result we get radius ratio is less than 0.414, and as we can see in this diagram the cation is not in contact to anion, and as a result of that, because anion both are negatively charged, they undergoes repulsion, and to stabilize that the cation connection is a must. So if the cation surface is connected to the anion, it will neutralize that particular thing, but here it is not occurring, and as the cation is not in contact to anion, you cannot expect perfect structure. So that is reason why if the size of a cation is lesser, so that radius ratio is lesser than 0.414, in that case this particular cation will prefer to occupy tetrahedral void whose radius ratio lies between 0.225 to 0.414. Second possibility, if the size of a cation is large, as a result this ratio, that is radius of a cation to anion, is greater than 0.732. In this case anion cannot touch one another, so we cannot expect a perfect solid, because we know that in a solids all particles are rigidly held together, but in this case as between anion more gap will be forming, so we cannot expect a perfect structure. As a result, in such situation this cation will prefer to form a cubic void whose radius ratio lies between 0.732 to 1.00. This is the table of radius ratio of different types of voids. So let us see a problem. The radii of Na plus and Cl minus are 0.95 angstrom and 1.81 angstrom respectively. Predict the coordination number of Na plus cation in NaCl crystal. Initially let us calculate radius ratio value, that is radius of a cation to the radius of anion. The value will come 0.524, as this value lies between 0.414 to 0.732. So the coordination number of sodium plus ion is 6 and it prefers octahedral site. The second problem is the radii of zinc plus 2 ion and sulfate minus 2 ions are 0.74 angstrom and 1.84 angstrom respectively. So predict the coordination number of zinc plus 2 ion in zinc sulfide crystal. Let us calculate radius ratio, that is 0.74 upon 1.84. As both the radius are in angstrom, that angstrom gets cancelled, so I have not written, and after solving this we get 0.40. as the radius ratio value lies between 0.225 to 0.414, so the coordination number of zinc plus 2 ion here is 4 and it occupies tetrahedral void. The third problem, the radii of cesium plus and Cl minus are 1.69 angstrom and 1.81 angstrom respectively. Predict the coordination number of cesium plus ion in cesium chloride crystal. So calculate radius ratio value, we get 0.93 as this value lies between 0.732 to 1. So coordination number of cesium plus is 8 and it occupies octahedral void. Thank you.